Hello and welcome to this clip on how to predict previously unseen organic mechanisms. It's actually a second version of an original video because since making the first video I found a few more examples that I thought might be good to put in here, so I've kind of redone it and extended a little bit to include them. So basically what we're going to look at is how to use recalled mechanism knowledge to try and work out what's happening in an unusual example you won't have seen before, because this is popular in organic exams. We've got to go back to what a curly arrow represents. The basic idea is it's the movement of an electron pair. So if we look at a common example from first year chemistry, excuse me, this is the beginnings of the electrophilic addition mechanism. So both those curly arrows involve the breaking of a bond because they move away from a bond, each of them. So that must mean a bond is being broken. So if we were to look at this one, this bond here, the pi bond within the carbon-carbon double bond is being broken. And 2 electrons move towards the delta positive chlorine. And the chlorine-chlorine single bond is being broken, and 2 electrons move towards the delta negative chlorine. Now the delta negative chlorine is delta negative because if you remember, there's a high amount of electron density in this double bond, which tends to repel the bond pair away from this delta positive chlorine towards this delta negative one. So it induces a dipole in what would previously be a non-polar molecule. So in the next half of the same mechanism, what's happening here is the curly arrow this time starts at a lone pair. So the lone pair alongside the Cl- it belongs to, the whole thing moves towards this positively charged carbon, or carbocation as we call it. The whole species here would be a carbocation. So this makes a bond. So the new bond being made by that curly arrow we just talked about is this one here. So looking at another common A-level mechanism, the electrophilic substitution. Now in each of these stages there's either bond making or bond breaking happening. What I'd like you to do is to pause the clip and see if you can work out what's going on in terms of bond breaking and bond making in each part of this mechanism, 1, 2, 3, and 4. Okay, welcome back. I'm assuming you've had a go at that. So 2 electrons leave the pi system at part 1 and move towards the nitrogen in NO2 plus. That's these 2 electrons here. So this carbon-hydrogen bond is going to break now, and this curly arrow shows 2 electrons moving into the partially delocalized pi system that's created when the fully delocalized pi system over here loses 2 electrons. So then a bond is formed between the carbon and the nitrogen. So that's the bond that's formed by these 2 electrons moving over here. This is the resulting CN bond that's made. So the proton is lost due to the breaking of the carbon-hydrogen bond. I'd like to take a moment here to just show you how the positive charge actually moves around the mechanism. It starts here, it ends up here, and then it moves on to here. So it's important to remember that when you're predicting what a mechanism might look like, if there's any positive charges involved, they need to not be discarded really, they need to be moved around the mechanism. Because basically what's happening is if a positive charge disappears, it's because electrons have moved towards where it was located. So therefore the positive charge will then end up where the electrons have just moved from, because that area will now be deficient in electrons. So let's have a look at an exam example. So I'll start with a multiple choice example. It says, what do curly arrows always show in reaction mechanisms? So because we've talked about this a bit already, it shouldn't be too difficult to work out that it's going to be B, C, or D. You can ignore A because that says the movement of 1 electron. So it's going to be the movement of a pair of electrons. So the thing to think about is electron pairs can be bonded pairs or lone pairs, can't they? So which answer covers both of those possibilities? It's going to be B, isn't it? So it's essentially the movement of a pair of electrons and nothing more. So our second example is a bit more involved. This is one you won't have seen before. So the curly arrow is moving towards the oxygen atom, and the oxygen atom carries a positive charge. So what they want you to do is suggest the structures that would be produced when that mechanism happens. So it says show the products. Now that means there's two things being made. So firstly, let's think about what's going on here. The curly arrow shows a C single bond O being broken and two electrons moving onto the O atom. Like we said before, if electrons move onto a positively charged atom, that positive charge goes away. And if electrons move away from something, that means a positive charge appears. So the electrons moving away from this bond that's being broken mean that this carbon here, where my highlighter is now defective or deficient, in electrons. So therefore, what's being made alongside that is a water molecule. So the positive charge on the O atom is gone because the O atom has received two electrons, and now we've put the positive charge over here. So like I said a moment ago, we're trying to track what happens to the positive charge as well and include that in our mechanism. So let's have a look at another example. So they want you to complete this mechanism by adding curly arrows in any missing species. So looking at what's happened between here and here, the first thing to notice is that C double bond O's become a C single bond O, and the oxygen has picked up a negative charge. They've also put in a lone pair there. So it must mean it's gained two electrons. So let's think about where they might come from in a moment. You've also got a carbon single bond oxygen that's been formed here that wasn't in place over here. So remember, this carbon double bond oxygen is polar. Although they haven't asked for them, you could imagine that there's a delta plus here and a delta negative here. So the delta positive carbon will tend to attract anything that's negatively charged, like a nucleophile, like our OH minus we've got there. Now the next thing to think about is, how do we justify C double bond O becoming C single bond O? Well, we give the oxygen atom two electrons, so the pi bond in the C double bond O breaks. And obviously if the hydroxide ion moves towards this delta positive carbon, it'll create a bond. Now in the bottom species, you can see there's no chlorine atom, so this chlorine has to come off. So therefore, the C-Cl bond breaks. Additionally, you've got C double bond O reforming, where it wasn't in place here. So this lone pair needs to go back onto this bond, like so. And obviously, the chlorine coming off becomes a chloride ion. Let me put that in at the bottom. So this is actually a very common mechanism. It doesn't come up in many A-level syllabuses. It comes up in some, but not in others. So if you're doing the OCR A chemistry specification, it won't be in your spec. If you're doing AQA, it will be, for example. So it's called nucleophilic addition elimination, and it's common in acyl chlorides and acid anhydrides. So basically, it's where you've got a C double bond O with something next to it, like that. So this type of functional group is prone to this kind of reaction. So our final example, this one's from an old spec OCR Chemistry A. I think it might have been 2015 if I'm correct, the rings, polymers and analysis paper. So they want you to add curly arrows to the diagram below to show the two-step mechanism of this species here. It's an aromatic carbocation with a fluoride ion. So let's take it each step in turn. So the first step is highlighted there, and this is the formation of the aromatic carbocation. So the electron pair must move from the bond between carbon and nitrogen there onto this nitrogen. So therefore you need to get rid of this positive charge. As you can see, the positive charge has gone from here to here. So an electron pair goes from here onto the nitrogen. So the carbon-nitrogen bond is also broken. So we talked a little bit earlier about what breaking bonds will look like in terms of curly arrows. So focusing on where the change has taken place. You can stick in a curly arrow like that. Now the next step is where you take the carbocation and you turn it into fluorobenzene. Just a quick note before we do that, the positive charge, like I said, has been moved around a bit. So remember, the positive charge has to be accounted for. We've just moved it from one place to another. So what has to happen here is the lone pair on the fluoride ion must move towards this positively charged carbon atom to create this CF bond. The nitrogen is no longer involved now because it's been created. The nitrogen molecule has been created. So what you do is you pop that in there like so. So if we look at our mark scheme, we can see what we've done matches what they've done as well. Okay, hopefully this has been a useful second look at how we do unusual mechanisms. Until next time, thanks for listening and see you soon.